Good evening, everyone. Welcome to the panel discussion on hammer and nail vis-a-vis AI, ML applications to network systems. The panel is going to be, the chair of the panel is a very distinguished researcher and also a practitioner, Dr. Praveen Bhagwat. Praveen Bhagwat needs no introduction in the world of Wi-Fi, wireless networks, communication networks. Got a very accomplished career behind him. He's a BTech from IIT Kanpur, PhD from Maryland College Park, and then spent several years in IBM T.J. Watson Research Center and AT&T Bell Labs. And then, of course, he was the founder of the famous Mojo Networks, co-founder of Mojo Networks, which has now recently been acquired by Arista Networks. So I have a great pleasure and a privilege of inviting Dr. Praveen Bhagwat to the stage to chair the panel discussion. Thank you.
Thank you, Rajiv. And as the initial fiasco told us, we are still a long way away from full automation as far as the networking systems and lives in general are concerned. But I'm really excited to be here today. And since we've lost some time, we will jump right into our discussion. So what I would like to do is to invite our esteemed panelists to the stage. Andrea, please welcome. And before we sort of got together to sort of come on stage, we had an internal email discussion going on among us. And what I want to do is to sort of present a very diverse set of views to this audience. And when I asked Andrea, how do you kind of rate yourself as far as this field of hype about AI ML is concerned? So I think her answer was, I am sort of cautiously optimistic. I was a non-believer, but recently I have discovered something which makes me feel excited about it. So we'll hear from her. Our next panelist is Manish. Manish actually was the head of Xerox PARC R&D Center here, then IBM Research Center, and he is a true believer. So I believe.
I also told you I can be the non-believer.
Well, so I think we will ask you to be sort of take both positions just to add more spice in our discussion today. Our third esteemed panelist is Rajiv. Rajiv, please welcome on stage. Now, what's exciting about Rajiv, I mean, he is, at Amazon, which is sort of the place which is shaking and moving the whole field. But when I said, what's your opinion about the AI and the human intelligence in general is concerned, so he said, no, he is mildly skeptical, the limits to which it can go. So I think we will hear some nice views from Rajiv next. And then Gautam, please come on stage. And when we discussed with Gautam, he actually said, well, he's sort of a bit detached, and he's going to see the big picture, tell us both sides of things, and we'll hear his sort of atheistic views. And finally, we have Professor Naren. And I think at the end, he'll have the advantage of seeing all the views, all the diverse views, and inject some sense of rationality in the whole debate. So I think without kind of losing more time, I will jump right into set the context for today's discussion. As we all know, AI ML area is sort of at the peak of its hype cycle right now. And if you come from a venture world, if you're thinking of a new cool idea, unless you throw these buzzwords in, chances that you'll get funded are very, very low. But the question which I want to pose in front of this audience, that what are the genuine applications that are amenable for AI ML style treatment as far as the field of networking is concerned? And just to kind of throw a bit of a contrarian view, if you look at the recent successes that this technology had in the area of face recognition, language translation, natural language processing, all the examples are outside of networking domain. So if it is really a tool technology which has tremendous potentials in our domain, then why we haven't seen something earth-shaking yet? And if something, great breakthrough is about to happen, let's hear what those ideas and areas are. So I'll invite Andrea first to start building up our expectation about the area, and then we'll have someone else to puncture the balloon, and that way we will kind of see all sides of this debate. So welcome, Andrea.
My slides.
Yeah.
Okay, so
The reason that I'm cautiously optimistic is because of some of the successes that we've had recently in my group, which I talked about a little bit this morning, on using machine learning at the physical layer in design. So the original title was, you know, can machine learning trump theory? We have an election in the US in about a week, and Trump is not the most popular word, so I thought I'd change it to beat theory. But really, as a theorist, I was very skeptical about machine learning for anything in communications, even at the physical layer, let alone the networking layer. I'm still skeptical about how it might be used at the networking layer, but we've used it, and I'll tell you where I think it might be useful at the end of this short set of slides. So, as I mentioned in my talk this morning, we've applied machine learning to detection of communication when you have either an unknown channel or a channel where the complexity of doing traditional equalization techniques is too high. So I started working on machine learning in the physical layer when we did this molecular communication I talked about this morning, where there's no channel model, because molecular communication, the molecules travel through the channel according to a diffusion process, so it's differential equations that are not the same as Maxwell's equations. And so in trying to equalize the intersymbol interference of the chemical communication channel, we tried machine learning because there was nothing else to use. When you don't have a channel model, there is no way that's known to do equalization. And it turned out that we got good results. So that got me thinking about machine learning at the physical layer, where I'm optimistic, not just cautiously optimistic, but very optimistic based on the results that we have. So the reason that machine learning is interesting in physical layer is because you don't need an underlying model. You can just train the algorithm or the neural network on a lot of data that you send across the channel, and even when the channel's not static, this works pretty well. So I'm not going to go into a lot of detail about this because we don't have a lot of time. This is just to give you a very high-level view. But we looked at the bit error rate for a molecular channel where there is no model, and for an optical channel following a Poisson distribution, so there is a model. And what we found is that I don't have a pointer here, but if you look at the blue line on the top curve that's going down, that's machine learning, whereas the red line, the blue line is Viterbi detection, so that's optimal for a known channel, and the red line is machine learning. So what you see is that machine learning beats the Viterbi detector, except when you have a very long length of the Viterbi detector. So when complexity is not an issue for Viterbi detection, then it's always going to be better because it's theoretically optimal. But when you have a complexity constraint on the Viterbi detector, machine learning actually does better. So one lesson from this is that when you have a complexity constraint, sometimes, of course, you're not taking into account the complexity of the training, but when you run the neural network, it works better. The other thing we found with the known channel of the Poisson model is that the other curves, the green and the orange, are when you use Viterbi detection, but you don't know the channel parameters perfectly, so you have some channel estimation error. And their machine learning also beats Viterbi detection. So the message is that even when we know the optimal theory, which is Viterbi detection, machine learning works better when you either don't know the model perfectly or you have a complexity constraint. And then in the case of the molecular channel where we don't have a channel model, again, machine learning does better than Viterbi detection. In the molecular model here, we are using the Poisson case. It has a much longer memory than in the optical channel. So machine learning does better almost always, except at the very end, when you have a very long memory length. And that's because the memory is so much larger, the complexity is so much larger, that unless you have almost infinite complexity for the Viterbi detector, machine learning does better. The other thing that we've applied machine learning at the physical layer to is joint source channel coding and source and channel coding. So here what we found is that because with text, there isn't a good mathematical model for text, and you can cluster things together by synonyms of words. So if you say an automobile is arriving and the car is coming, those are similar clusters of text. It turns out that the machine learning does better than separate source and channel coding, use the most sophisticated compression, Huff encoding gzip, and Reed-Solomon codes. So using the very best channel coding and the best compression for bits, actually machine learning does better. Now we've dug into this a little bit more, and it turns out most of the gains are coming from the compression. And the reason for that is what I said before. We don't have good mathematical models for text compression. So when we don't have good mathematical models at the physical layer, machine learning is better. So I'm going to just touch on where I think the work that we're going to do in my group looking at machine learning for networks comes in, and that has to do with network resource allocation. So here is a problem where, again, we don't have good solutions to doing the optimization. It's a non-convex problem, it's very hard, and there are patterns that you can see by running these networks and training on data. So I do believe that a place to look for applying machine learning in networks is this network resource allocation. The challenge is formulating the problem. So neural networks, again, they work very well when you can formulate an input-output of a system and say, this is something that I want to optimize, and run lots of training data. How to fit this optimization problem into that problem formulation is what we're struggling with right now. We don't have the solution. So going back to why I'm not optimistic, and where my skepticism comes in, is how in network optimization do we formulate these problems in a way that's suited to neural networks? What is the input? What is the output? What is the data that we're training? So I talked about this fog-based optimization. This is with standard optimization techniques. We see that we can run the optimization on neighborhoods, and we get a small performance penalty relative to centralized optimization. The next step here is to say, okay, well, what if we apply the machine learning for the clustering only? How do we cluster the base stations together? So that's a problem that I think we can pose as a machine learning problem. The resource allocation problem is harder. I think if we could formulate that, we might be able to apply machine learning in a powerful way to this very non-convex, NP, really hard problem of network optimization. So that's my position. So I'll say I think machine learning is a powerful tool in our toolbox, but it has to be used with care. That's where the skepticism comes in. It isn't that every problem that we're trying to solve can be solved with machine learning. In fact, I think most can't. So the biggest challenge for this community is identifying which problems we can apply machine learning to. We've seen at the physical layer that it works well when we don't have channel models or we don't have channel parameters. Is that true with system models overall? So networks are very complex. Maybe that's where the sweet spot is in applying machine learning. And so bandwagons, which machine learning is a bandwagon, they can be fun. We've had a lot of fun working on it so far, but they can also be dangerous. If you just look at this as a tool that we can apply to everything, no, we need to use the knowledge that we have about solving these problems using traditional techniques to figure out how to apply machine learning to them in a way that's successful. So that's all I have. Thank you.
So although I was counted as a believer, yeah, so let me start with kind of acknowledging the wise words that we just heard from Andrea, because we have reached a point, because at this point, we're almost at a point where it doesn't matter what the problem is. The solution is machine learning. And not even that, I mean, usually deep learning, because machine learning is kind of passé, right? It's not good enough. It has to be deep learning, no matter what the problem is. So can I also have the browser? Can we start with the browser first? So I've been personally interested. I mean, I'm not a machine learning expert, neither a networking expert. So what am I doing here? I mean, I've been very interested for the last, I would say, at least 4 to 5 years in looking at how technology gets applied to important problems. And the two problems that I consider the most important, at least for India as a country, would be education, learning, and the other is healthcare. And so I'm going to argue why I believe, again, in both of these fields, there's a huge
potential for transformation that can be brought about with the help of machine learning. And while I view, okay, so you're trying to get this Wi-Fi. So we have the right man for the job, who's setting up the Wi-Fi. Browser. So I'll start with, again,
What is where you want to
this conference website. Can you get to that? Yes, I sent you that link. Do we know the conference?
Actually, can
website?
we,
Yeah.
maybe this computer is not even on the
Okay,
net,
okay.
so
So
I think
it's not. Okay, so so I won't give you the live demo. So there was some connection between learning and networking, which is this conference on networking. So I was going to bring up the web page of MobiCom. And if you look at the videos on MobiCom, already there are a bunch of videos which are now being played using our player. And I'll tell you how we have applied AI, again, machine learning for that. So in learning, to me, given the problems of lack of good teachers and so on, and so many millions of people who need to be given the right education, skills, and so on, obviously video-based learning is a very promising path. And the big problem with videos, anything other than entertainment videos that we have, is that somehow human mind is not wired to let us watch these videos. We start getting distracted very, very quickly. We can watch movies for hours. We can watch cricket games in India for hours. But if it's a video lecture, even on a topic that we care about, video topic, lecture on machine learning, I want to learn about machine learning, after a few minutes, my mind starts wandering elsewhere. So we then drew inspiration from textbooks. Because in some sense, videos are the next generation of textbooks. And textbooks, you don't give a textbook to a person and just expect them to read it cover to cover. Textbooks come always with a table of contents. So usually people look at the table of contents and then say, okay, here are the topics which are being covered in a book, and I'm right now going to just focus on reading this particular chapter. So why should it be any different for videos? So we started applying, again, artificial intelligence to automatically start generating this table of contents for all of these learning videos, and in general, any informational video. And it's a very hard problem. So far, we have made some progress. I mean, we have a bunch of US patents, conference papers, and so on, and still our techniques work only kind of reasonably well on a limited class of videos. So when I'm using slides, we are able to automatically, by applying, again, machine learning, we are able to automatically classify those video frames and say, okay, which are the video frames which represent a unique slide being presented. And then from that slide, from that frame, I do a bunch of other classifications and so on, and I'm able to infer, okay, which is the box which contains the text, and then do OCR and read out the titles. So we do that table of contents. The other thing about books is the index at the end. So we also do speech recognition over the entire video, and we give you a searchable transcript. But out of those thousands of words that the speaker might have uttered, what are the top most important key phrases that the speaker talked about? What were the key concepts that the speaker covered? Again, we try to do that automatically by applying machine learning. And all of this, we kind of keep the mapping so that both of these indices, they give you a summary of the topics which are being covered. And then if you're interested only in a specific topic, let's say supervised learning, I just click there and it takes me to that part of the video. Or if you look at any of these concepts in the phrase cloud, you can just say, okay, I want to know where the speaker is talking about whatever, one of these concepts, and it tells you all those places, and you're able to just go to that part of the video, only consume that part. And our data, all the ACM webinars, the recordings are being played using our player, and the data that we have collected shows that not only do you allow people to now find what they're looking for, the actual amount of time they're spending on the videos is actually going up. Because normally, the video viewing pattern is like this. There's an exponential decline after the first few minutes, which is why most video lectures are kind of by Coursera, edX, and so on, you'll find are like just a few minutes long. And we say we don't do that with books. We don't distribute 100 booklets to the student and say, okay, look, you want to read about this topic, learn about this topic, here are the 100 booklets. You present a book with a table of contents and so on, so it should be similar. So that's all I'll talk about for learning. Healthcare, I'm no longer working on healthcare, but the topic fascinates me from some of the work that we did at Xerox. It's a broken system all over the world. I don't believe there's a single country that has figured out and has a really nicely functioning healthcare system. Because today what we have for the most part is a sick care system. If you look at a country like US, it's very expensive. In fact, there was this famous doctor who famously asked this question at a healthcare conference. He asked the question, where do you find the most expensive place to stay overnight? And the first thought that comes to everybody's mind is a fancy 5-star hotel in one of these fancy exotic locations. And he said, no, it's the ICU of a typical hospital where you'll be shelling out over $10,000 for spending that night. And for all you networking guys, yes, that's heaven, because the person is all hooked up with all kinds of sensors. There's a sensor for blood pressure, temperature, heart rate, all kinds of things. And you're trying to save the person, but it's not a fun experience for the person, and it's a very expensive place to treat the patient. So therefore, the way to transform healthcare with higher quality, as a compiler guy, I look at it as very analogous to the compiler optimizations we used to do for memory hierarchy, right? You want to serve as many of the references, data references, out of register or level 1 cache. If they can't be done from register or level 1 cache, L2 cache or L3 cache or main memory, not to go to the disk. It's a similar thing with healthcare, that you have these very expensive tier, ICU. That's the most expensive tier. Yes, there's something more expensive, which is the graveyard, point of no return. So you don't want to let that data access be served kind of beyond the ICU. So you want to save lives. And again, there are opportunities for you to apply machine learning to save lives. Because today, the state of the art, pretty much of commercial systems, when you're trying to predict complications in an ICU, is very carefully handcrafted rules that the doctors have created, and often they don't work very well. They lead to too many false positives, and therefore, the real practitioners ignore most of these alerts. So there's an opportunity to really ultimately analyze data and machine learn these models. Yeah. But back to the story, I mean, if not the ICU, ideally you would like to take care of the patient before they enter the ICU, or even earlier at the primary healthcare center, or even earlier. So I believe most of the action in healthcare in the future is going to move outside the hospital. Just like we talked about flipped classroom, it's going to be flipped hospitals.
So Manish, in the interest of time, I'll
okay.
sort of
So I'll stop with maybe just one last example. So in home, there's an opportunity now for us with all these sensors. It could be wearables, it could also be cameras, that you could really apply machine learning, for instance, also to infer body vitals, like your heart rate and so on from cameras, and then start to apply these models to start predicting potential complications and take proactive action for the individual before they need to kind of go for expensive treatment. So proactive action is a great way, ultimately, to help us achieve higher quality in healthcare at lower cost, and this is where I believe down the road, machine learning can make a big difference, but it has to be combined ultimately with scientific, it has to be also combined with scientific models and scientific simulation. Thank you.
Thank you, Manish. So I think I'll invite Rajiv to reflect on his thoughts on why he believed that the area of networking hasn't yet benefited
from the advances in ML space. And I think while we are debating this, we had a live example of one, there you go, that we had the previous laptop all set up to show everything.
And at the last minute, we switched the laptops, which wasn't even configured to get onto the network. So these are the real life problems of network management. Why there is still so much of human intervention still required. And we'll, I think, figure out if ML has a solution for these real problems in life, in our lifetime.
Okay. So I work for an e-commerce company, and we're using machine learning. Whoops, what happened? Whoops, did I? Okay. Okay, sorry, I just moved it. Yeah, so, and we're using machine learning across our business, right from mundane things like determining the most cost-effective packaging for a product to a lot of customer-facing applications such as product recommendations, ranking of product search results, as well as predicting ad-click probabilities. For retail companies, being able to forecast the future demand for products is important. We use machine learning even to predict the lowest competitive price for a product. So even a lot of product prices are currently powered by machine learning at Amazon. And we use machine learning to improve the quality of our product catalog, classifying products into large taxonomies with tens of thousands of leaf nodes. And of course, all of you know, or most of you have probably interacted with Alexa. Alexa is completely powered by machine learning, right from voice recognition to natural language understanding to carrying out conversations with end users. So there's numerous success stories of machine learning in various companies. So I used to do networking work. I worked on network management a long time ago when I was at Bell Labs. And I was just looking around on the web, and clearly there's a lot of research that's been done on applying machine learning to networking. Network performance monitoring is an area where ML can be used to forecast future traffic demand. In fact, AWS does need to do capacity planning, and they need to predict what sort of demand there is going to be for different services. Machine learning can also be used to predict the throughput for a user session, so that perhaps you can buffer the right amount of video before you start playback. And of course, classifying traffic into different applications so that maybe you can prioritize certain traffic and so on. Network security is a big space, and I'll talk about one or two applications that we are actually using machine learning for within Amazon. Clearly, bot detection is important, detecting denial of service attacks based on the distribution of IP addresses, number of requests, types of requests, again, classifying flows into malware or viruses based on flow characteristics like your average size of packet, inter-packet arrival time, flow duration, number of bytes in a flow, and so on. So the whole host of different applications in network security, clearly fault management and identifying root cause of problems. There was an interesting paper from Google on configuring data centers so that you minimize the power consumption within the data center. Essentially, they were using machine learning to try and predict the data center efficiency based on data center operational parameters like the number of chillers that are operating, heat exchangers, pumps, and so on.
So
and
Rajiv,
course,
if
yeah.
I may inject a sort of a
Sure.
different thought in what you're saying. I see web scaler companies have very effectively applied AML to streamline their business operation. But this technology still hasn't
Right.
into the enterprise space or in our layer 1, layer 2 routing protocols or design
Sure.
tools.
Yeah.
And so wondering, is there something about the structure of those problems that we deal with in the communities such
Right.
as MobiCom and SIGCOM?
Sure.
That
In my last slide, I'll touch upon some of the challenges. Clearly, not all of these are all potential applications. Many of them haven't really been realized, and I'll talk a little bit why I think some of these haven't been used, or why machine learning hasn't succeeded in some of these applications. Just moving on, I'll quickly talk about some of these applications. At Amazon, we're using machine learning again. In India, the wireless network bandwidth is patchy. We want to try and predict what kind of latency end user is going to experience, and based on that, download the appropriate content for the user. So we'd maybe drop some widgets, drop images if we found that the bandwidth is going to be, if we predict that the bandwidth is going to be very low based on the network type, device type, location, time of the day, and so on for the user. Detecting bots, I talked about this. There are bots who try to break into accounts, or there are bots who do ad-click fraud. So trying to detect whether traffic that's coming to your site is from a bot is again an area where we use machine learning. Here we use many different features. We build a signature for what normal users are like based on the query rate, the click-through rates, time they spend on pages, their browse behavior, and so on. And if we see outliers in this feature space, we recognize them as bots. So again, the challenge here is this is an unsupervised learning problem. You don't have labeled data. You really don't know what are bots and what aren't. So the whole technique here is around clustering and finding outliers. Again, identifying machines that are infected with malware based on communication patterns, how many bytes are they transmitting, receiving, number of flows, what are the different ports they're accessing. So we, in fact, have built models to try and identify machines that may be infected on AWS. Identifying root cause of problems. And we have an interesting parallel to this in Amazon, where we have a delivery network. And essentially, packages get stolen in the network, and we really don't know who's stealing the packages and where they are being stolen. So we use machine learning, again, algorithms to try and identify where exactly packages may be stolen. So there's a lot of parallels to just finding out where there may be a network problem, where there's a link that's down and so on. I talked about data center efficiency prediction, again, using different data center operational parameters and trying to predict what would be the best configuration for a data center to operate at the optimal power efficiency. Again, Andrea talked a little bit about compression. So this is, again, another idea that we are pursuing at Amazon, is to try and use an autoencoder to generate a latent space representation of images, and then compress images using that latent space representation. Just to conclude, a whole set of technical challenges still remain. While there are many successes, I think perhaps in networking, ML hasn't picked up as much because I think networking applications, especially when you look at packet classification and so on, really require a very high level of performance, and machine learning models still, I think, making predictions, you aren't going to be able to do these at the kind of speed or wire speed or line speed that may be required for applications such as routing and so on. Of course, machine learning models aren't perfect. They make learning errors. And in the real world, this could really have a high cost. If you're looking at self-driving cars or even network operations, if you misconfigure devices in a network, hell could break loose, and you could actually bring down the entire network. So there are some risks here because no machine learning model is going to have 100% precision. There's also issues related to obtaining label data, especially if you're talking about bot detection, fault detection, and so on. There's very little data out there on faults. Of course, you don't want to bring a production network down or inject faults into a production network just to create training data. There's a whole lot of other issues around generalizing. So all your models need to generalize to different topologies. The networks are dynamic. And so on. And of course, learning many times, because your networks are dynamic, you need to explore. And exploring different, perhaps, configurations or different routes could lead to network instability. So that makes it also very, challenging to use machine learning in networking. And the final point I have here is really around, there's a lot of hype around neural networks, but these are really essentially black boxes. And in many cases, you do need explanations for actions you may take. And so that's again another problem. If you're going to, suddenly shut down somebody's account saying that they're a bot, you need to give a proper explanation, or you need to have an explanation of why you're doing that. And many of these models can give you explanations, and so their applicability becomes a lot more restricted. And
So
one final point I would say is, really, I think you need the full power of machine learning and neural networks when you're really dealing with semantics. There are very challenging problems, AI problems out there involving summarizing content, right? Take a book and generate a summary. That really requires you to understand the semantics of the book and so on. I don't think networking has problems of that level of semantic complexity for which you probably need neural networks. I think networking in many cases requires very high performance and perhaps more like classification or maybe simple rule-based systems. So that also, maybe networking doesn't need machine learning for every problem out there. And maybe there is a small set of problems in network management and so on. Operations is where ML could fit well.
Or maybe the type of problem we are dealing with in networking can be captured by some precise logic where you don't need this whole fuzzy space where you have to throw data to have a neural net to learn.
Right.
And maybe it's too mission critical. So you don't want
Right.
the
Yeah.
networks to make some false...
Yeah, I think machine learning, one of the problems also is very high false positive rates, which makes you have a lot of false alarms that people are sifting through. And so I don't think ML has ever succeeded in fault detection and root cause analysis and so on, just because the false positives and the false alarms are just way too many.
Thank you. So I think we'll open the floor for more comments and questions from the audience. But let me ask Gautam to kind of summarize his view.
So I don't have charts, so it'll make it easy to keep it short too. Firstly, I was just thinking about the. I told Rajiv that look, I don't know much about networking. But I just remembered just now that in a book I wrote 5 years ago, I have a page or 2 pages on the analogy between basic Shannon information theory and an ML system, because it's all about mutual information between what you want to predict and what you actually can observe using the data in the model you create. So model is a form of compression in the end, right? And in the end, you want to maximize the mutual information of that and whatever you want to predict. So it's very similar to information, Shannon information theory. And the excitement, if I can summarize in one sort of related to this audience analogy, why is there excitement? Well, we've been doing, machine learning, statistics, AI, data mining for a long time. The excitement is that, for all of these techniques had a certain capacity. I mean, beyond a point, you really can't go too far with a traditional statistical model. The excitement is that now, suddenly, in the past 4 or 5 years, it seems that by throwing more data at deep learning models, its channel capacity sort of seems to be, there's no bound. You can just throw more and more data, and if you are good enough at it, and you can have enough computing power, you can get better and better and better. And that sort of generated some amount of excitement. I'm an atheist because I don't think that excitement by itself should be measured against a traditional technique. We need to look at traditional techniques together with whatever we're getting from this new way of doing things, and get the best of both worlds and essentially solve the problem. So let me talk about a couple of problems that we are solving fairly successfully. One is data center management. In 2015, we launched a product called Ignio. It's on the web. It now has over a couple of dozen enterprise-grade customers. It manages data centers quite automatically. It starts off obviously just by monitoring, and then decides what's going to happen next in terms of a potential fault problem or a potential failure, and then when is it going to happen, and then it allows people to propose fixes, and if you do something, then what would happen if you did this, is the right fix or not. So you have, in some sense, a twin of the center or data center. And then if you want a particular outcome, what should you be doing now? It's sort of a short-term and medium-term planning. Now, this data centers are very complex. They can have thousands of servers, many different networks, sub-networks, all different types of components, various different types. So now you really can't be thinking of throwing a huge neural network at all this, can you? I mean, it will not work. You won't have enough data, even if you let the data center run forever. So you'll have to do it at a component level, and then fundamentally, you can do this using traditional statistical machine learning models, and you can do that fairly well. Recently, we started using deep learning in some of these components as well. We've done exactly the same thing for different types of plants, real manufacturing plants, refineries, power plants, totally different product. It has a name, we call it process equipment analytics and control. It's not launched, so it doesn't have a formal trademark name. But again, the models are different. They're data driven. There's anomaly detection using deep learning. There's remaining useful life prediction using deep learning. There's regression models which are using statistical techniques. There is a whole bunch of things, but the whole point is that the analogy is similar, and you're doing the same, answering the same kinds of questions. Is everything okay? If something is wrong, what's wrong? When is it going to be going wrong? If I do something, will it fix the problem or something else? And if I want a particular type of control, operation, optimize power, optimize pollution, whatever, what should I do? And what's the best thing to do given current conditions? But it's a very different domain. So that's why I feel that in networking domain, similar things can be done, and actually are being done some time back, maybe a year or two. We looked at a company called Arya Networks. It does this. You can look at it on the web. It does this for a network. And it uses various types of AI. I won't tell you exactly what it uses because that was a confidential investigation. But it's doable. But now, as I mentioned, and as Rajiv also mentioned, that we can do all these things using theory, and theory you can do it using statistical techniques. But why? What's the excitement about new types of techniques? I'll tell you three important things that we've learned. One, it's very surprisingly, learning from deep learning models which are trained on a variety of different scenarios, time series from machines, from people, from engines, from cars, and you train models using all this data, and you have a model, and you have features. And using those features, you can actually do better than models trained on only one particular type of data, and especially have not enough data. So there's quite amazing, this concept of ImageNet and how it works on images, pre-trained models. So pre-trained models is something which is exciting. You just don't have that in traditional models. The second is multitask. You train models on multiple different tasks, and they all do better than being trained on just one task. There's also something which never was sort of observed in traditional AI ML. So this is also quite exciting. And the third extremely surprising thing to me was there's this optimization, very well established field. You can throw CPLEX at problems. You can do MILP. You can do convex optimization. You can really solve problems really well. But you solve it today, and then you solve another problem tomorrow. You start from scratch. Reinforcement learning just keeps getting better. And in 2017, Nando de Freitas had a paper which showed that actually, using RL, you could beat a whole bunch of good optimization techniques, including ML-based Bayesian optimization techniques. So, I mean, there's something interesting. It's a sort of a meta-learning. You're learning to learn how to optimize. So these are the causes for some amount of excitement. At the same time, there are a lot of challenges. First of all, of course, explainability, Rajiv mentioned. But then there's also the issue of a bit of sort of calibration. You don't know when you're right or wrong. Unlike a statistical technique, you have good error bounds. These things have very bad error bounds. There's some work on calibrating machine learning models, or deep learning models, but it's very difficult. So it can be very confident it's right, and it's absolutely hopelessly wrong. So you don't have good error bounds. The second big challenge with these newfangled techniques is that how do you compose? How do you create a large, complex system? It is not really clear how to do this, right? You obviously can't just put them together in boxes and bolt them because the errors will propagate. So how do you tune and how do you flow, right? So those are difficult problems. And how do you, in some sense, deal with meta learning? The third problem. How do you deal with learning across different instances when the dimensions change? You have 50 sensors now. You have 1,000 sensors tomorrow. There are ways of doing this. We're working on it, but these are important research challenges, and we're making some progress on this area. And I don't think people have really done this.
So Gautam, I think thanks for...
Last point, explainability. There's a huge need to bring logical techniques into these kind of machine learning models, right? And it's not that I'm not the only guy saying it. Google DeepMind is doing that with inductive logic programming and deep learning. So all this stuff is making a lot of things exciting. Yeah, go ahead, Praveen.
Yeah. So I just want to pose a kind of a question to you that the whole space of ML, I see sort of two communities of people. There are statisticians who are bringing a lot of statistical learning concepts in here. And then there is a whole deep neural net based breakthrough. So do you see that maybe statistical learning approaches have a more applications given the nature of the space we are dealing with? Or because often the terminology gets overused. I mean, when people throw the word ML, it actually is now become a buzzword.
I mean, a Viterbi algorithm is basically a HMM, and that's all you've been using all this time in coding, right? So it's a statistical learning technique. And as Andrea said, that you can do a little bit better with deep learning models, and that's something interesting going on over there. So there is an evolution. So I don't think that there's an either or. There is an evolution, and there's more deep learning happening now. There is a marriage of some of that and statistical learning theory, but it's still two different worlds. There's a deeper marriage of that going on, and more good old-fashioned logic-based AI, because that's really required. The higher levels of deep learning don't really do logic too well, but how can you actually use perceptual sort of things at the lower level and logic things at the higher level? That's really probably where we need to go.
I think what we'll do is quickly
I think
finish
that's
the
all I
last
had to say,
perspective,
right?
and then invite some questions from the audience as well. I'm giving you Rajiv giving signals that we have to wrap up things within time to go over for dinner. So let me invite the last speaker to reflect.
So I have the advantage of not having to repeat what everybody else has said, and just try to put an envelope or sort of convex hull on what people have said. Okay. So let me first, so this is about AI ML for networking problems. So just to keep ourselves anchored, let me just go back to the first course in AI. What does it say about AI, what it is? AI comes from natural intelligence, and it is almost accepted notion if you look at the classical textbooks in AI, that AI integrates the data input, perception, reasoning about the data, senses in our cases, and then using the results of reasoning to go back to the world. So this loop of perception, reasoning, and action, that's where the name artificial intelligence comes from. And if you look at any of the AI literature, I mean AI, not ML, it will tell you that it's representation, representation, and representation. Because once you represent it right, everything else becomes more or less trivial. And that's where really the human intelligence lies, that's where geniuses lie, and intuition lives. So classically, if you look at the evolution, it was feature space, which really was the representation. And in AI, you make the what you're trying to do very explicit. The representation really has a direct relationship to the problem you're trying to solve. And then, so you have explicit models, they're specified, and the models may be of different kinds. They don't have to be one size. They can be deterministic, structural, statistical, symbolic, signal level, time varying, stationary, that's all fine. But there is a set of models. How you use them is where specific techniques come in. But it remains true that you have separate, very clearly separate stages which correspond to perception, reasoning, and action. You look at any AI algorithm, classical algorithm. Now, let's talk about ML. First of all, today, what is being seen as ML, which is deep learning and neural networks, is not what ML started out to be. ML started out to be as given a dictionary of models, whatever those models are, like I listed earlier, you formulate your problem as a composition of these things, decompose your problem, and that was done mostly by humans. So you are not going into the atomic level detail, but you are looking at the big picture, like a graph, which tells you what kind of interrelations there are between entities. Entities themselves are your own intuition's creation. So you sort of represent it in a reasonable way, and that makes the second level problem much less complex. You have to evaluate them individually, and your interaction is predefined in that sense. It's kind of like if you have a sawtooth wave, and if you want to capture it using frequency spectrum, it would be really difficult, but if you, it'll have very complex energy distribution, but if you divide it into the line segments, the whole thing becomes trivial. You can represent each segment in a nice compact way and capture the discontinuities separately in the representation. Now, so I'm going to take ML as it is viewed today as neural nets, because today's students don't even know some of the other ways of doing it. So in today's NN, the problem level is, so it's an end-to-end operation at the problem level. Give me a problem, I will shove in the stuff, and out comes a result, and I'm going to learn the relationship between the two. The stages, the classical stages of perception, reasoning, and action are all jumbled up into one, and you're expected to relate those two end to end. So this is where the sawtooth division is sacrificed, and you're trying to get a good way to describe the complex spectrum, which is made complex by you. The problem doesn't demand it, not easy to understand. And the reasoning is correspondingly hard. So as far as the AI, classical AI goes, because of that representation, there is room for performance analysis. You can sort of push your performance analysis through these stages. And with neural nets, surprises are possible because you have pushed everything into one end-to-end thing, and you cannot quite track what is happening where. So surprises are possible anytime, because you really don't know what exactly is going on.
So I think in the interest of time, what I want to do is quickly, if we can get to a round where we start inviting feedback and inputs from the audience as well. So
and these surprises are likely to increase as you apply it to more and more problems. Because in a way, the neural nets do the deep learning networks do nearest neighbor search, more or less. So as your neighbor density increases, meaning when you apply it to more and more problems, it's going to be difficult to include only the right answers, because your envelope that captures the right things will also include in it bad points. So finally, with the problems that we have seen, networking problems, you can, all of these problems, you can have correspondence with classical AI formulation where there are agents which interact, which have certain relationships. So you can map every single one of these problems onto this representation of agents interacting in certain ways, agents having their own properties, and therefore, the AI performance, neural net performance aspects can be related to the performance of the networking performance of them in the networking situation. And so NN will work as long as there are problems are sparse and no accidents have been seen, and therefore they can be used very well. However, they have to be used as tools which are set in this setting of representation, which has to come from human experience, or even they can be derived separately. It doesn't have to be done completely by humans. That can be derived. So there'll be two stages of inferring the structure and then using whatever tools, including neural nets, which are very good, as long as they are done at the individual segments of the sawtooth.
Yeah, thank you. I think one of the challenges I see with doing work in the ML space that you need actually access to some very high quality data to be able to train any logic that you're trying to perfect. In the field of networking, I think this advantage that the web scaler companies had, that they had access to that data, it was properly labeled, and they could leverage that to essentially get some breakthroughs. If you are a university professor, you have your campus network, I think there are challenges. I've talked to many IT folks at universities. There's a bit of a reluctance to use the campus network as a source of data, because there are a lot of privacy issues around, if you start tapping into my traffic, are you going to be looking into what's going on? So there is a sort of a barrier to using that available resource to feed into the ML research. And in general, the quality of the data and the type of labeling that you need to be able to train networks is just not available. So I'm curious, among us, the people who are working on ML applications in networking, where are they sourcing the data from? Because without the real high quality data, how do you really get the breakthroughs that you're looking for? And I'm curious to kind of have the panelists reflect on this and also start inviting questions from the audience in terms of what are the key challenges that they see as far as working more in this space. Because I think if you look at the network management space today, and I think we spent a little bit of time talking about it, I think that's the one domain that I see where there is very compelling applications out there.
There are those challenges of not getting access. I think that's a matter of a people issue, actually, and I think one can solve that problem. But there's a bigger problem, and that is that if your networks are good, things don't go wrong too often, and then you don't have enough data by nature. So you need to marry real data with simulators, reduced simulator from 25 years ago, whatever, and you really need to be able to generate anomalies yourself using your theory and marry those two together. Otherwise, you'll never get enough labeled data. And in terms of labels, you should also be looking at new techniques of generating soft labels like Snorkel from Chris Ray's group at Stanford and things like that. So there are ways around it, but bringing theory in is important.
So one of the problems with network optimization as a sub context of network management is that we haven't formulated those problems well, even for traditional techniques. We don't have good problem formulations for if we want to say, let's optimize the network. because I've been working on that problem for a while. It's an intractable problem. We don't have good models. We don't have good optimization frameworks. So how can we apply any tool, machine learning or otherwise, when we haven't formulated the problem well? And I think that that's at least what I see as one of the big challenges of applying machine learning or any technique to that optimization problem. I would broaden your question when you say, well, you know, why hasn't machine learning had impact on network management or network optimization? Well, we haven't been able to even get baby steps on solving that problem well with traditional techniques. So I think until we do that, we're not going to be able to apply ML.
So first of all, let me take a controversial stand. I believe the problem of less data or not enough data is overrated. It's not true at all. The reason we are not getting enough data is because we don't know what we want. We just want to have all large amount of data, and then we want to fit something in it, like the neural net, and it wants a lot of data. So unless we understand what the problem is like, unless we formulate it, this problem will continue.
So I think one comment, Andrea, what you said. What do you think about anomaly detection? Because that's, I think, one problem domain where it's possible to think of ideas where you baseline the way your network is operating, and any deviations from that baseline is something, if you can automate that, it will certainly add value. Because today, if you look at network operations, a lot of it is manual in terms of people looking at the consoles and so. And I think I recently kind of read an article where a person had an interesting perspective to offer that if you look at an image recognition problem which has been cracked by ML, a 5-year-old, whatever the 5-year-old, 10-year-old can recognize by looking at the picture, that's the level of intelligence we've been able to capture in the deep neural net. Now, what this technology does is gives you ability to do these kind of decisions at a very mass scale. So if we had a capability to automatically detect some anomalies in the network through its logic, and if we could scale it up, what more we could do in the network at a larger scale. I think that's one area where we can start maybe thinking. But I think maybe anomaly detection is an area where I think, you see, today the state of the art in networking, network management is that still 80-90% of the enterprise IT administrators processes are very much manual. I mean, so the DevOps has moved into the cloud backend, but not in the enterprise IT.
So two things you have to be careful when you are doing anomaly detection or whatever with, let's say, machine learning. One is, as some of the cybersecurity people found out, there are then newer ways that people come up with, right, to do attacks, where you're not really engaging in anomalous behavior. You try to blend in with almost normal activity, right? That you don't just attack the system and start leaking information. You kind of lie low and then slowly leak information so that the anomaly systems just miserably fail at detecting that kind of a, let's say, break-in. So that's one caution. The other is, by very definition, right, a lot of these failures, anomalies and so on, as Gautam also mentioned, are very rare. So that creates that class imbalance problem, which is a huge issue for machine learning. People still haven't been able to effectively solve for effective classification when you have this huge class imbalance problem. It affects a lot of healthcare prediction, for instance. So it's a good thing for us as humans that most of the time, I mean, if you're trying to predict, am I going to die? Am I going to have this very deadly cancer? It's good for us as humans that the odds are very, very low. But that creates a challenge to the machine learning person, because now, even if I have a little bit, I mean, if I have 99% sensitivity and specificity, which sounds amazing, the number of false positives is still going to be far higher than the number of true positives that I catch. So it creates that big challenge. So even in anomaly detection, it's not like a smooth sailing.
I think in the interest of time, I will put a stop here and would like to thank all the panelists. We have a small token of gift from ACM. So let me present our first panelist with a small token. Thank you. Manish, thank you.
For that wonderful panel. On behalf of the ACM MobiCom 2018 Organizing Committee, it's a great pleasure, to Praveen, great pleasure to have you as a panelist. Thank you all very much for the wonderful panel. I think it's a pretty current and a catchy topic, important topic. At this point of time, again, let's thank the panelists once again for an outstanding panel. Thank you, Praveen, for the wonderful panel discussion.